Welcome all. This is e-lecture series on machine design. In mechanical engineering, we have already learned engineering mechanics and strength of materials. Now we will be learning machine design. The three subjects are very much related to each other, mainly engineering mechanics, strength of materials, and machine design. They are related in the sense that in engineering mechanics, we learn the concept of force and moment acting on bodies. We have also seen when a number of force and moment act on a system, how to find the resultant force. That is, we learned the basic concept of force and moment. And when we have a body, when a series of forces are acting, now we have seen how to find the resultant force acting at any point in the body. Also, we can find what is the resultant moment acting on the body. Also, the necessary condition for static and dynamic equilibrium of body was also dealt in engineering mechanics. This is a very fundamental and important concept. That is, for static equilibrium of body, the summation of all the forces acting on the body should be equal to 0, and summation of all the moments also should vanish. That is, if it is a two-dimensional problem, you have sigma fx is equal to 0 and sigma fy is equal to 0 and sigma m is equal to 0. These are the conditions for static equilibrium of a body. So this we have seen in engineering mechanics. Also, we have seen the central concept of moment of inertia. In strength of materials, we have used the concept which we learned in engineering mechanics, and we have advanced to the next level. From the forces acting on a body, we could now estimate what are the stresses. That is, in strength of materials, using the concept of force, we have found out, or we have estimated what are the kinds of stresses which comes in the body. Stresses, when I say stresses, basically two types of stresses: normal stress and shear stress. And we have also seen what are the kind of deformation which comes in the body. When different types of stresses act on body, like in combined loading, where you have combination of normal and shear stress. That is, if I draw a state of stress of an element, it will be represented like this, where sigma x is the normal stress acting in x direction, sigma y is the normal stress acting in the y direction, and tau xy is the shear stress. When such kind of a stresses act on a body, then we have also seen how to find the resultant stress or the principal stress. This is a very fundamental concept which we have learned in strength of materials. That is principal stress, which is nothing but the maximum normal stress experienced by the body. And in such cases, if a body is subjected to such kind of a loading, the maximum normal stress, which is represented by sigma 1 or sigma 2, will be greater than sigma x and sigma y. Therefore, when we do the design, we are going to consider what are the principal stress coming in the body. So therefore, the concept of principal stress is very important as far as machine design is considered. Also, under such kind of a loading, we have seen what is the maximum shear stress coming in the body. tau max experienced by body, maybe this may or may not be equal to the tau xy. And in design of this component, we are going to consider this maximum shear stress as well as the principal stress. Therefore, the concept of principal stress, which we have learned in strength of materials, is going to be very, very relevant for machine design. And how do you find the principal stress coming in the body? That is using the concept of Mohr cycle. That will be we'll be discussing in detail later. Now, once we know the concept of stresses coming in the body, which we have learned in strength of materials, now we come to machine design. In machine design, we use a concept learned in strength of material. Basically, the stress estimation under the system of load. So, in machine design, what we are basically doing is using the concept of stress coming in the body under the system of loading, we try to design the machine element to take the load without any failure. This is what we are going to deal in machine design. Therefore, now we have seen that all the three subjects, the engineering mechanics, strength of materials and machine design, are very much related to each other. Since they are very much interrelated, before starting the course on machine design, we will have a recap of what we have learned in engineering mechanics and strength of materials. Okay, the first session of this course will be theories of failure. The first session of this course will be theories of failure. This will be completed in 5 modules. In module 1, we will be seeing what is a stress and strain, the basics, which you have already seen in strength of materials. In module 2, we will be seeing how to draw the stress strain diagram. And what is the strength of a material. In module 3, we will be dealing with stresses in machine element. In module 4, we will be dealing with the principal stress. And Mohr cycle. And this principal stress is the most important and the most interesting concept in strength of materials and machine design. And it is very, very relevant in designing any component. And finally, in module 5, we will be seeing what are the failure theories. So therefore, we will start with module 1, which is nothing but the basic of stresses and strain. So what is stress? When an external force acts on a body, suppose I have a body like this, it's a rectangular specimen, and I am exerting a force on both sides of magnitude P and the unit is newtons in SI units. And when such kind of external force acts on the body tends to elongate or deform. And the internal forces are developed in the body which tends to prevent the elongation. So when this force is acting, internal forces are generated within the body. So when I take a cross section, when I draw the free body diagram of section 1, what I get is, I have the force P acting here and some internal resisting forces are acting on this cross section. So internal forces which resist the deformation are called the resistive force, given as R. And the resistive force acts uniformly across the cross sectional area. That is, if I draw a cross sectional area here, it will be acting uniformly over the entire cross section area. And this resistive force developed per unit area is called stress. So stress is equal to resistive force per unit area. All these concepts we have already learned in strength of material. This is just a recap of the strength of materials. And this stress which acts normal to the cross section is called normal stress. Therefore, stresses basically are of two types. One is called normal stress and this is called shear stress. And the stress which we have seen in this figure here, this figure, it's a normal stress because the stress acts normal to the cross sectional area. And shear stress is a stress which acts parallel to the cross sectional area. This will be seen in detail later. And again, the normal stress are of two types. One is a tensile stress, one is a compressive stress. Tensile stress is a stress resulting from increase in length. From an increase in length is called tensile stress, and the stress resulting from a reduction in length is called a compressive stress. So in this above case here, the stress coming is tensile stress because it is trying to elongate the specimen. Therefore this stress is a tensile normal stress and it is a tensile normal stress. And when the forces acting on the body, as we have already seen, the body has a tendency to deform or elongate. When the force is acting, what happens to the body? Body which is initially of a length L will undergo deformation by a amount dl, and we have a new term strain, which is defined as the change in length to the original length. Therefore, in this case, we can see what is the change in length. It's dl and original length is L. Therefore, what will be the strain? Strain will be the change in length dl by original length L. And as we see in stress, here also, since the strain is normal, it's called a normal strain. And it's a tensile normal strain. So here we have seen the normal stress sigma is given by the load per unit area and the normal strain epsilon is given by the change in length by original length. Okay, so what is the relation connecting these two? This we will see later in stress strain diagram, but I will just explain. In stress strain diagram, we can see that when the material is loaded up to the yield point or elastic limit, the stress is directly proportional to strain, or we get normal stress is equal to E into epsilon, where E is called the elastic modulus or the Young's modulus. And this equation is called Hooke's law. This we will see in detail when we talk about the stress strain diagram. Now we will see the second type of stress, basically the shear stress. As I have already mentioned, shear stress are the stresses which acts parallel to the cross section. Suppose we have a body like this, which is fixed to the ground, and I am applying a force P parallel to the ground. So what happens to the body? Body has a tendency, since it is fixed to the ground in the bottom. Now we will see the second type of stress, basically the shear stress. As I have already mentioned earlier, shear stress are the stresses which acts parallel to the cross section. Now suppose if we have a body like this, which is fixed to the ground, and a force P is acting on the top surface. Since it is fixed to the ground at the bottom here, since it is fixed here, what happens when we apply a force like this? The body has a tendency to slide, causing an angle of phi. The body will slide on the top surface will be moving ahead and the bottom will be fixed to the ground. This kind of a motion is called the shearing. And here, if A is the cross-sectional area of the specimen, we say the shear stress tau is equal to P by A, that is nothing but shearing force by cross-sectional area, and phi, which is the change in angle between two surfaces that is if I write this as OA A dash, P B B dash, or I'll write the Q. So initially, so lines OA and OQ were perpendicular to each other. Now OA has come to the position OA dash and OQ is still remains as OQ. So what is the angle now? Angle now is this angle, which we say as some theta dash. So what is the change in angle from 90 degree to theta dash? That is given by phi. Phi is nothing but, here initially it was 90 degree and currently it is theta dash. So phi is the change in angle between two surfaces originally perpendicular to each other. Is that clear? That is phi. The angle phi, this angle phi is the change in angle between two surfaces, this surface and this surface, which were originally perpendicular to each other. And the tangent of this angle, tan phi, is called the shear strain. So shear strain we call it as gamma, is equal to tan of phi. So we have shear stress as P by A, and the shear strain is nothing but tan phi. And similarly, similar to the normal stress, here also the shear stress and shear strain are related to each other. And shear stress is proportional to shear strain, and the constant of proportionality is nothing but G, and G is called the rigidity modulus or shear modulus. And I have seen that many of the students have a difficulty in understanding what is the shear stress. So in order to explain in a more easier manner, we can take two plates like this, which are fixed by means of a bolt. By a bolt and nut arrangement. Now we are applying a load P, trying to pull the two plates apart. When we are trying to pull the two plates apart, which are joined by means of a bolt, shown here, what happens to the bolt? Now we will draw the free body diagram of the bolt. How it will look? If I draw the free body diagram of the bolt, so I can say the force P acts on the top part and the force P acts on the bottom part. And if this bolt is actually a circular cross section, now the bottom portion you have a force P acting towards right, top portion P acts towards the left. So what happens? How does this bolt fail? The bolt will fail at this cross section, which is shown here. This cross section is prone to failure when load acts like this. So how it will fail? We can draw the figure like this. So as shown here, the bolt will fail into two pieces about this cross-sectional area. So now are you able to visualize how the shearing is taking place? Shear takes place about this cross-sectional area. So what is the shearing cross-sectional area here? If D is the diameter of the bolt, the shearing cross-section is nothing but pi d square by 4. And the shearing forces P. So what is shear stress developed here? Shear stress tau is nothing but P by A. That is nothing but P by pi d square by 4. And that is nothing but 4P by pi d square. That is the shear stress. So I believe that by this example you will be able to appreciate what is shear stress. And the most important thing which I find missing in the students is they are not able to visualize what is the shearing cross section area. So whenever you have a doubt with the shearing, you just think of this example where the bolt is getting sheared into two pieces and the shearing cross section area is nothing but the area of the circle, that is pi d square by 4. Now having learned about the normal stress and shear stress and normal strain and shear strain, now we will see what is meant by state of stress at a point. The state of stress at a point in the material is a representation of all the stresses acting at that point. Suppose we will take the first example which we have studied, where a rectangular specimen is subjected to a load P on both sides. Suppose if we take a cross-sectional area, draw the free body diagram of the left half. What we can see is, you have the force P acting here. Now if I take a small cube here, in this cross-section area, like this, if I expand this, what I get? This is the cube, and what will be the stress acting on this cube? We know that normal stress is sigma given by P by A, and if the coordinate system is like this, x, y and z, you have sigma x equals P by A. Since it is a one-dimensional case, you will have sigma y is equal to 0 and sigma z is equal to 0. So you can represent this sigma x, and your all shear stresses, that is tau xy, tau xz and tau yz, all will be equal to 0. So the state of stress of the element will be like this. So this will be the state of stress of the element. Now suppose if you have a three-dimensional body with an arbitrary shape, large number of forces are acting on the body. Now what I do is, I take a cut here. Now if I take a small cube here inside this and I expand that, it will have all kinds of stresses. That is, in all planes there will be stress. You suppose this is the coordinate system, this is x and this is y. You will have sigma x on the left and right surface, sigma y on top and bottom, and sigma z on the front and back. And what about the shear stress? And another very important thing is, the shear stress is denoted by two variables. Like if I say tau xy, I mean this is nothing but shear stress acting on the x plane in y direction. This is very important. So tau xy is the shear stress acting on the x plane in y direction. So again, if I take the cube, the same cube I will be drawing once again. Okay, now tell me, which is the x plane? X plane means, what is x plane? X plane is the plane whose cross section area, whose normal to cross sectional area is parallel to x direction, x axis. So in this case, this is your x axis. And what is the normal to a cross sectional area? Like if I have a cross sectional area like this, what will be the normal? Normal will be, it's perpendicular to this area. So perpendicular to this area, if I draw a line here, it will be in the y direction. So what about this plane here? In this plane, if I draw a normal, outward normal like this, it will be acting in the x direction. So this is nothing but the x plane. And in x plane, the normal stress acting is sigma x. And what is the shear stress acting? It will be tau x, and this is acting in which, this shear stress is acting in which direction? This shear stress is acting in the y direction, so we call it as tau xy. We have one more shear stress, which is nothing but tau. It's x again because it is acting the x plane, and z direction, so it's tau xz. So this should be very clear. Tau xy means the shear stress acting on the x plane in y direction, and tau xz is the shear stress acting on the x plane in z direction. Similarly, we will see the y plane here. The normal stress acting, it will be sigma y, and what will be the shear stress acting here? Shear stress will be tau y x, because it is acting on the y plane and it's acting in the x direction, so it is tau y x. The other shear stress will be tau y z, because it is acting in the y plane and the direction is z direction. Therefore, we have three stresses acting on each plane. On x plane we have sigma x, tau xy and tau xz. In the y plane we have tau yx, sigma y, tau yz. Similarly, in the z plane we have tau zx, tau zy, sigma z. This gives a totality of the stress acting on this cube. So this is called the state of stress at the point. So this matrix is called the state of stress at this point. Why do I say point and I have drawn a cube here? We have taken, as we have seen here, we have taken a very small cube of distance, say dx, dy and dz being the sizes of the cube, and when this sizes of the cube becomes 0, that is when dx, dy, dz tend to 0, this cube will tend to be a point. And then this matrix will represent the state of stress at that point. So this is about the state of stress at any point. So now, if we have a point, I can draw infinite number of plane passing through that point. That is, I can draw a plane like this. I can draw another plane like this. If I have this point, I can draw another plane like this. Like this, I can draw infinite number of planes passing through a single point, and it can be seen that in the strength of materials books, if you see once again, you can see that the state of stress, if you know the state of stress at any point, state of stress at any plane passing through a point, then you can find out the state of stress in any other plane passing through the same point. So the details of this are available in Advanced Mechanics of Solids, but right now this level of concept is sufficient for machine design as well as strength of materials. So that is about the state of stress acting at any point in the body. So given any kind of a loads acting on a body, we should be able to find what is the state of stress of any point. Suppose, as an example, I'll say if I have a same rectangular plate, I am having the force P, and I am trying to give a torque T. I am giving a couple twisting couple C. So what will be the state of stress? Now if I take a small cube inside the specimen, what will be the state of stress? If I draw the cube here, it's a two-dimensional problem. Now what will be the stresses acting? Due to the force P here, I will have a normal stress which is given by sigma, and I can write it as sigma x since it is two-dimensional. And what about sigma in two-dimensional case? What all the stresses? What all stresses we will have? We will have sigma x, sigma y, and tau xy. And here I need to mention one more thing, that the tau xy is same as tau yx by the principle of complementary shear stress. Complementary shear stress principle. This is already dealt in engineering mechanics, so I'm not going to deal it in detail. So tau xy is same as tau yx. So in a two-dimensional case, we have three stresses, which is sigma x, sigma y, and tau xy. So given such kind of a problem, first thing you have to see is you need to find the three stresses, sigma x, sigma y, and tau xy. And what is sigma x? Sigma x is the normal stress acting in the x direction. So in this case, you can write sigma x is equal to P by A. What about sigma y? Do you have any load acting in the y direction? No, we don't have any load acting in the y direction. So we can write sigma y is equal to 0. And what about tau xy? Tau xy is the shear stress. Since you have a torque acting here, twisting couple acting here, you have a shear stress which is given by tau is equal to T by J into R. So this tau will be acting in which plane, in which direction? So it will be acting in the x plane in y direction. So we can write tau xy. And what will be the value of tau xy? Tau xy will be Tr by J. Sigma x will be P by A. And sigma y will be 0. So the state of stress at a point, if somebody asks, you can say, you can draw it like, so state of stress will be sigma x, tau xy, sigma y. This will be the state of stress. So this is nothing but P by A, Tr by J, Tr by J 0. This will be the state of stress for this case. Similarly, you should be able to find the state of stress for any kind of a load system. Now I have given a very simple example of a normal force acting and a twisting couple acting. So we have only normal stress in x direction, which is P by A, and the shear stress which is coming because of the torque T, which is given by Tr by J. And there is no force acting in the y direction, so the normal stress in the y direction will be 0. So this will be the state of stress at that point. So once you are able to calculate or able to predict what are the stresses acting on this body, mainly sigma x, sigma and tau xy, it will be very, very helpful in understanding what will be the principal stress, because once we are able to find sigma x, sigma y and tau xy, once we are able to find the state of stress acting on the body, then only we will be able to find what is the maximum normal stress and maximum shear stress coming in the body. So this concept is very important. This will be the foundation for understanding the principal stress concepts. So this completes the first module on basic of stresses and strain. So we have seen what is a normal stress, what is normal strain, what is shear stress, shear strain, and what is state of stress at a point, and about Young's modulus, shear modulus. Then we have seen how to find the state of stress at a point for a given load system. Now in the next module we will be seeing how to draw the shear stress strain diagram. That is another very important concept, which introduces a new concept called the strength of the material. This we will see in the next module. And for this module, the reference book for this module will be the Mechanics of Material by Timoshenko. It's a foreign author book, but you have an Indian edition. And I would like to say that this book is very, very, it's written in a very easy manner. It's very easy to understand this book. Many people feel that Fallen Order book is very difficult to understand, but this book is written in a very simple manner. So in case of any doubts, you can just go to the Strength of Mechanics of Material by Timoshenko. This completes the first module on basic of stresses and strain. And in the next module, we will be seeing about the stress strain diagram, how to draw the stress strain diagram, and a very important concept of strength of the material, how to evaluate, and what is the difference between strength and stress. So those things we will be seeing in the next module. And for the first module, which I have already covered, the basics of stresses and strain, the reference book will be The Mechanics of Material. I'll remove this portion. This completes the first module on basics of stress and strain. In the next module, we'll be seeing about the stress strain diagram, how to draw a stress strain diagram, and we'll see about an important concept of what is the strength of a material, and what is the difference between the strength of a material and the stress in the material. And for the first module on stresses and strain, I have referred the book by Timoshenko. It's called The Mechanics of Material, shown here. Mechanics of Material by Gear and Timoshenko. It's a Fallen Order book. It's a very easily understandable book. So it's a very useful reference. So in case of any doubts, you can go through this book. Thank you.